This is Bill Farmer again. Welcome back to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. These are going to be the components of this topic. What is first-order logic? The syntax and semantics of first-order logic, axiomatic theories, truth versus proof, Hilbert-style proof systems, and Gensen-style sequence systems. Okay, so the first topic is what is first-order logic? So, first-order logic is a study of statements about individuals. And an individual can be almost anything. And these statements are constructed using functions, predicates, Boolean operators from propositional logic, and quantifiers. And first-order logic is also called first-order predicate logic or first-order quantificational logic. So first-order logic we can think of as propositional logic plus terms that we use to denote individuals, the things we're talking about, and predicates that can be applied to terms, and quantifiers that can be applied to individual variables and formulas. Notice I said individual variables. These are variables that range over individuals. First-order logic is first order because quantification is over individuals, not over higher-order objects like functions and predicates or sets of individuals and so forth. So, the foundations of first-order logic were developed independently by Gottlob Frege and Charles Sanders Peirce. Frege was a German, Peirce was American. These are probably two of the greatest, if not the greatest, logicians of the 19th century. There are many formulations of first-order logic. There's many ways of doing this. We're going to follow how first-order logic is developed by Ben Ari in his book, Mathematical Logic for Computer Science. Okay, so the first thing we're going to do is talk about the syntax of first-order logic. So we're going to start by letting V be a set of symbols, and this set will be countably infinite. So the point here is that this set V is countably infinite. The reason for that is we never want to run out of variables. No matter how complicated of a statement we make, we always want to make sure we have plenty of variables. So a first-order language is going to be a triple. It's going to consist of a set C, a set F, and a set P. C are going to be constant symbols. They're going to denote individuals. F will be a set, script F is a set of function symbols. They denote functions. And script P is a set of predicate symbols. They denote predicates. Remember, all a predicate is a function that gives a value of true or false. Now, each of these function symbols and predicate symbols is going to have a superscript, which is going to give the arity, how many arguments it takes. And quite often, we'll just drop this superscript when we know how many arguments are involved. And so now we have four sets. We have the set of symbols which are variables, constant symbols, function symbols, and predicate symbols. These are all disjoint. What that means is there's no symbol that's in more than one of these sets. And now we can define the first category of syntactic objects, terms. So a term is a set of strings inductively defined by the following two rules. Every variable is a term, every constant in C is a term, and if F is a function symbol of arity n, and T1 and through Tn are terms, then F of n applied to T1 through Tn is a term of L. And this actually should say term of L here. Okay, so that's what terms are. Terms are variables, constants, or their applications of function symbols. Well, we're not done with the syntactic yet. We have to talk about what formulas are. Now, an atomic formula looks like this. It's an application of a predicate symbol of arity n to n terms. So that's an atomic formula. And the set of formulas are all the strings that can be inductively defined by the following rules. Each atomic formula of L is a formula of L. If A and B are formulas L, then all the formulas we can get by applying the Boolean operators, they are all formulas of L. And then the third one is if X is a variable, A is some formula of L, then for all X dot A and there exists X dot A are formulas of L. And these two formulas, so this one here, this is known as a universal formula, and this is an existential formula. Okay, so let A be a formula of some first-order language. A universal or existential formula is either, as I said, it's either this or this. So a universal existential formula, that's this or this, is called a quantified formula. X is the quantified variable, and the scope of X is A. So the scope of X in both of these is A. A is a formula. It can include the variable X. Now we'll say an occurrence of X in A is free if X is not in the scope of a quantified variable X. So for instance, if I have something like this, X is not free. In fact, we'll say X is bound because it's in the scope of this variable X. Y is free because it is not in the scope of a quantified variable. And we'll say A is closed if it has no free variables and is open if it has free variables. And if the free variables of A are x1 through xn, the universal closure is a formula of this form. So basically we quantify all of these variables, and that will mean that these variables that are free in A, they will not be free in the universal closure. Now I want to mention a notation which I don't use that often, which is A with a bunch of variables in parentheses. This is a way of indicating that A is a formula and its free variables are included among these variables. So that's a common notation that people use. Okay, so let's talk about substitutions. So a substitution of a term t for a variable x in a formula A, we write it like this. But there's many ways people write this. Sometimes people write it like this, or like this. And it can be rather confusing because there's so many different ways it's written. Anyway, if you have a substitution of t for x in A, it's the result replacing each free occurrence of x in A with t. So if I had a formula like x equals y, let me write it right. Well, let's just go to it. Let me just go up here and get a... So if I had a formula like x equals 2 and x equals 3, and I'm going to have a substitution where I replace x, so t, let's say, is 5. This is going to equal 5 equals 2 and 5 equals 3, which, by the way, we would expect would be an invalid formula. Okay, so that's the idea. That's what substitution is. Now, there's this technical definition we need, which t is free for x and a if no free occurrence of x and a is within the subformula of this form, where y is free in t. So when we replace x with t, that t should not be in a subformula of this form. If it is, that means that because y is free in t, that y that's free in t will now be bound in this formula. So if y is in here and if x is in here and I replace x with t, now this y will bind the y in t. Okay, and so here's a simple example. Y is not free for x in this formula, because if I substitute y for x here, it becomes bound by this. Now, we say that a variable capture occurs in a substitution of this form if t is not free for x and a. So if t is free for x and a, we won't have a variable capture. If t is not free for x and a, we have a variable capture. Now, variable captures need to be avoided because they lead to results that are not correct. And there's basically 3 ways to avoid variable captures. The first is I define this substitution here only if t is free for x and a. That's one way. The other way is if I have a variable capture, I rename the variables. So if I was trying to substitute y for x here and I get this variable capture, I could rename this to z and rename this to z. And then when I substitute y for x, we do not have a variable capture. The third way is we use a different set of symbols for free and bound variables. Okay, now variable captures are the cause of many mistakes in logic. It is the classic mistake that is made in logic, is to allow variable captures to occur. So when you're dealing with substitution, you have to be very careful that you do not allow these things to happen. Okay, so I want to talk a bit about variable binders. A variable binder you can think of, I'll write like this. It's a special operator that's applied to a variable and an expression. I'll write the expression like this. And this variable binder, it basically binds the values of x to a certain collection of values, depending on the kind of variable binder. Okay, so that's what a variable binder is. And in logic, the most common ones, which we have seen already, we have in first order logic, universal quantification and existential quantification. Another variable binder is lambda for creating functions. And there's also a variable binder for definite description and indefinite description, which we'll talk about down the road. Now, variable binders, as I've just mentioned, for first order logic are universal quantification, existential quantification. Variable binders occur throughout mathematics. Basically, whenever you have a construction where you have something that is a dummy variable, that's a variable that you could change the variable, make it something else. You have a variable binder. So the dummy variable in iterated addition is x in this case. Iterated multiplication is x. In substitution, the dummy variable is x. In integration, it's x here. When you have a limit, it's x, and x here. All of these are variable binders, and they all use a dummy variable that could be swapped out, and we could use a different variable. Okay, so we're going to stop here, and we're going to continue with the semantics of first-order logic in our next lecture.